A little demonstration of the experiment before you head off and run your own one.
Okay, so first things first, I am going to cut up my apple. So first of all, I'm going to slice it in half, and then I'm going to make some small pieces. I slice it in half again, and I'm going to cut it really small. And again, don't worry if you don't have an apple, you can be doing this with a potato or lettuce or banana, as I've said. So we're going to cut it again. Make sure we've got really thin pieces of apple. I'm going to cut it again. So look, and you've got nice small chunks of apple just like this. So I've now got 4 pieces of apple. I'm going to cut another one as where I've got, need to cut another 2, so let's cut this one. Okay, so now I'm going to put pieces of apple into each of the bowls. This one is my control, so this one is not going to have anything in it, we're just going to leave that just as apple. This one here is my bicarbonate of soda. I've got my bicarbonate of soda here. Next one is the orange juice. So I'm going to chop up my orange. The next one is my lemon juice. So I've got my lemon juice here, but you could be using lemon juice from an actual lemon or bottled lemon juice. And if we compare to the bicarb, we've got a very similar amount of liquid in here. Next one is our milk, so we're going to pour that in. And lastly, we have the vinegar. I'm going to pour that one in as well. So that is our experiment, nicely set up. So it's time for you to go ahead and be scientists and run your experiment. So you need to leave your experiment for 1 hour. Go and do something else in that time. There's plenty of things you could be doing. If you haven't done our sensory science video, you can go and find that on our website or on the YouTube site. You could read a book, you could do some colouring, go and tidy your bedroom, lots of things you can be getting up to. Okay, so your 1 hour is up, everyone. It's now time to see what your experiment looks like and how much browning you have. So I'm going to get you to pause the video before we go ahead and explain the results, and I want you to write down what you've observed, go back to your hypothesis, see if you're right, and have a think about what you saw. You could maybe even write these down in a results table so that when we come back and do the explanations, you can have a think about why your results are as they are. So I have my results in front of me, and we're now going to go through the science behind our browning experiment. So I'm just going to tilt my screen so that you can see my samples in front of me like this. These are my samples, and I will lift them up to the camera when it's time for us to go through them. So starting with the control. So this was my control that had no treatments. We can see the browning spots here. If I turn it over, we can also see the browning spots there. And I've got a picture coming up in the corner of our control. So this had no treatments, and this is what we are comparing all of our other samples to. So starting off with the lemon juice sample. This for me was the least brown. So if we look here, we've got no browning occurring. So the lemon juice, first of all, is very acidic. So lemon juice is pH 2, and that is very much below the optimum pH of our enzyme, which is pH 5 to 7. So it inactivates the enzyme. We're not able to have our reaction between polyphenol oxidase and oxygen occurring. But another really interesting thing about lemon juice is really high in vitamin C, which is also called ascorbic acid. And ascorbic acid is an antioxidant, and by antioxidant we mean something that will preferentially react with oxygen. It will use up oxygen. So normally polyphenol oxidase can react with oxygen to produce those brown pigments, but here we're finding that the ascorbic acid will actually react with the oxygen before the polyphenol oxidase can do that, meaning there's no oxygen left for the reaction forming the brown pigments, and so that's why our lemon juice sample is really not brown. And similarly, the orange juice, although it's a slightly higher pH than the lemon juice, we've still got no browning, and that's again because orange juice is really high in ascorbic acid, and therefore the oxygen will preferentially react with the ascorbic acid, and we're not getting that browning reaction occurring. So I'm now going to move on to the bicarbonate of soda. This for me was the most brown. So if you look, it's really, really brown here, and it's really brown here. So it is pH 9 to 10. And it's really alkaline, and that means it's got an abundance of hydroxide ions, so OH minus ions, as opposed to our acid samples which have abundances of hydrogen ions. That means there's actually more oxygen for our polyphenol oxidase to react to, meaning that we get a quicker reaction. I'm then going to move on to my milk sample. So I had a little bit of browning in our milk, so we can see that there's a little bit of browning here, and if we compare it to our lemon juice, you can see that there is a little bit more browning in our milk sample. That milk is around pH 6 to 7 depending on your milk, so it is within the optimum range for the polyphenol oxidase. However, it is not really alkaline, so we're not getting an abundance of hydroxide ions, but we're still able to have the browning reaction occurring, although it is slower than the one with no treatment. And that's probably because the milk is covering the apple slightly, which means that there's a little barrier for the oxygen to have to get to the apple. So lastly, moving on to our vinegar reaction. So the reason why we left this till last is because we actually had a really unexpected result. It went really brown, and even more brown than the control, which is something we did not expect. So if I show you our vinegar sample, it looks something like this. Look at all this browning all over here, and if we compare that to our control, you can see just how brown it is. Now, I don't know about you, but I expected that because of the low pH of the vinegar, approximately pH 3, it would have inhibited or denatured the enzyme, with the enzyme being a protein, and slowed down or completely stopped the browning reaction. And as you can see, that didn't happen at all. So, being scientists, we repeated this experiment twice more, so we had 3 samples to go from, and each of these still remained brown. More brown than the control, and more brown than the bicarbonate of soda reaction. So then I did some research looking at the ingredients in our vinegar, which was distilled malt vinegar. And malt vinegar comes from barley, and barley grains actually have a really high level of phenolic compounds, like we talked about earlier, so the compounds that can make blueberries blue and can provide carrots with their orange colour. Now, because they had such a high concentration of phenolic compounds, it meant that we had a really increased concentration of substrate, because if you remember in the reaction, it's the phenolic compounds that are reacting with the oxygen, and that reaction is catalysed by the polyphenol oxidase, and therefore we're able to have a much larger extent of browning because we have such an increase in substrate concentration as we put quite a lot of vinegar in the glass. So that probably will explain why we had such browning when we used the malt vinegar. So I tried it with another vinegar as well, and that was white wine vinegar. So if I show you that one, look like this. So we've got around about the same level of browning in the white wine vinegar as we do with the control. White wine vinegar contains sulfites, which inhibit the reaction as they are inhibitors of the polyphenol oxidase. So what we could see from this is that it's not just the acidity that affects this reaction. We're getting effects from antioxidants, so they are really slowing down the reaction or stopping it. In the lemon juice and the apple juice sample, we're having inhibitors like the sulfites in the white wine vinegar. And we're also seeing that substrate concentration, so the concentration of phenolic compounds, really plays an important role in this reaction. Okay, so finally, we now know that polyphenol oxidase can cause brownings in fruits and vegetables. So why do you think that PPO is important in the food industry? Why does it matter? Pause the video, have a think about what you know about polyphenol oxidase, and write down a few reasons why you think it's important to both the food industry and to plants. Have a think, pause it, and we'll come back and discuss in a minute. So, I don't know what you've written down, but some of you may have said that polyphenol oxidase might be a cause of food waste in the food industry. And that's because if you were to buy a packet of cut up apples and you saw that they were brown, I don't think you'd want to buy them because you'd think they didn't look very nice. And so polyphenol oxidase, if this browning reaction happens during the processing of fruits and vegetables, can lead to a lot of wastage because then they can't be sold in the shops. So we have to work out ways to inactivate the polyphenol oxidase, and that's either by using a really high temperature, as I explained, that polyphenol oxidase is inactivated by high temperatures. For example, if we're cooking like apple sauce, we'll make sure it's heated really high to inactivate the enzyme. And secondly, by adding in preservatives or ingredients. So the next time you buy guacamole, you might see that actually on the back of the packaging it will contain lemon juice or ascorbic acid. And that's vitamin C and lemon juice added in to inactivate the polyphenol oxidase and prevent your avocados going brown. The same as when you buy cut fruit in the supermarket, it's often dipped in a preservative solution which prevents it from going brown. Otherwise, we'd end up with really spoilt and low quality and not very nice looking fruits and vegetables, which wouldn't be very appealing for you and I to buy in the supermarkets. Now, you may have noticed that if you have a plant that's split off or a leaf that's broken, that you get some brown spots or some brown patches on the leaf. Now, that's because it's been broken off and the polyphenol oxidase, just like in our food, has been exposed to the air, so you're allowed to have that browning reaction occurring. Now, we don't know this for definite because, well, I've never spoken to an insect, I don't know about you, but it's been thought that insects are actually deterred from eating the leaf anymore because of the brown colour, so it prevents any more destruction to the leaf. I hope you've really enjoyed today's video. I hope you've learnt something, and the next time you see a brown apple in your lunchbox or the next time you see a potato going brown on the side, you can tell your friends and family why that is. Stay tuned for our next video, which is going to be looking at use by and best before dates and how to understand them better to reduce food waste. Bye everyone!